everyone, I'm Lucy, and as we said, I'm from the University of Sheffield, and I'm quite lucky to be following that talk because they've done a lot of the legwork in explaining what high entropy alloys are and why they're useful. But let me just give a quick outline. So I'll briefly explain about high entropy alloys, why they're useful, why they're used so much in AM, and I won't go into that too much because of the last talk, but in case anyone joined us. I'll then be talking about what you can do when you have some high entropy alloys and you need to be able to assess their AM processability without the need to buy bespoke expensive powders. And I'll talk about the welding process that I've developed in order to be able to do that. I'll then talk about how we've verified the results from this process with some known high entropy alloys which we've manufactured previously, and drawing the parallels between the results of the weld tracks and the results of the AM build. I'll then talk about some of the novel high entropy alloys that I've developed and the results of those weld track trials, and then talk a little bit about some ongoing work which involves some modelling to go alongside those weld tracks. So, very briefly, high entropy alloys contain, well, this is the initial definition which was proposed at their discovery. So, they contain at least 5 principal elements at 5 to 35 atomic percent. However, the alloys I'll be presenting only contain 4, so I'm already ignoring this rule. They're predicted to have a stable solid solution because of their high configurational entropy. However, this configurational entropy isn't always enough to hinder the formation of intermetallics, but it's a good bet sometimes that high entropy alloys will have that stable solid solution, and that in turn helps with that AM processability. They also, as you can see from this graph, which is very similar to the one that was shown earlier, they have some desirable material properties. And that's to be expected because in the high entropy alloy design space, even with 4 component alloys, there's over 1 million possibilities. If you increase that to 5, 6, 7 components, you have billions of alloying possibilities. So the space to tailor your material properties is very interesting. But obviously, it's a bit like finding a needle in a haystack, so we have to find some methods in order to narrow down that haystack to just a hay bale, and then we try our best from there. So why are they so looked at in AM? Well, we've done some work previously on the cobalt chromium iron nickel system, and often these alloys, because of their stable solid solution, show a really good crack susceptibility. So just to illustrate that, this alloy had 99.9% density at an optimum VED, and when you decrease that, it shows rock effusion, and when you increase that VED, it shows keyholes, but at no point does this alloy crack when you process it by AM. They also, as with a lot of alloys, show increased strength when you manufacture them by AM versus casting, and that can be tailored by heat treatments as well. So this is as cast and as printed stress strain curves. So when we were thinking about designing our high entropy alloy, we realised that most of the literature involves taking a known high entropy alloy and putting that in your AM machine, doing a design experiment, and seeing what you got out at the end. There's very little literature on designing a high entropy alloy for an application and for a process. So our application is an extreme environment heat exchanger. I've taken this from the literature as an example. And we need to be able to manufacture this by AM. So our operating temperature is at over 1200 degrees. We obviously want a low density alloy because it's for an aerospace engine. And crucially, we're looking for a single or multi-phase solid solution because, well, for 2 reasons. One, we're trying to mimic the possible multi-phase alloys that you see, like conventional superalloys, and we're looking for that weldability. So at this point, I have this huge alloy space, this huge haystack, and I need to be able to narrow down those alloy compositions. So with lots of alloys, you'd maybe turn to machine learning or something like that, but with high entropy alloys, the amount of databases, well, the size of the database is quite small, it's quite inconsistent, and when you then move to weldable HAs and AM, that size is even smaller. So we had to use some of these which were outlined in the first lecture of this session, and we found some alloys which had a stable solid solution. We also found some which weren't so good, had a lot of intermetallics and some immiscible elements. So I outmarked 9 samples, and out of the 9, 5 of them went forward to the next stage. So far I've shown you these 2 bits of the flow diagram, and I need to get over here. But I have 5 novel high entropy alloys, and I don't want to make 5 bespoke new powders because that times my research budget is not big enough for that by about a factor of 5 to 10. So we had to come up with an intermediate stage, and that involves weld tracks in conjunction with modelling. And because I'm mainly an experimentalist, I'll be looking at the weld tracks today. So the weld track methodology. I took an arc-melted alloy sample as cast because I wanted it to have a microstructure as close as I could possibly get to an AM microstructure. Sectioned it in half, mounted it, and then put it into our Econity mini machine at the University of Sheffield in an argon atmosphere, and then did weld tracks which look a bit like this. So within each weld track set, there's 5 or 6 hatches, and we did a designer experiment much like you would do with a new alloy, but just with weld tracks, and vary the laser power and scanning velocity. So how do I know what I'm seeing in the weld tracks is representative of what I would see if I looked at these alloys by AM? Well, this is a result of the weld tracks. We have a beautiful mosaic image here, and some of these alloys show brilliant weldability under every condition. However, we also had some samples which looked more like this. So cracking under every single welding condition. And here's a zoomed in image of what that looks like. So, as I was saying, how do I know that these are representative of what I would see in AM? Well, previous work we've done has been on some in-situ alloying of elemental powders with a cobalt, chromium, iron, nickel base powder. So we already have some history manufacturing high entropy alloys from using AM. So we also did weld tracks on these alloys, and I'm going to draw some parallels now. So first of all, we have the pre-alloy powder with copper, and this alloy shows extensive solidification cracking. It's a 2-phase FCC alloy. So this is what we see in the AM part, and you can see here, shown by the orange arrows, that we have quite a lot of solidification cracking for low energy density and high energy density. We also have, in high energy density, some solid state cracking, and that is reminiscent of what we saw for this alloy in high VD samples far away from the build plate, so at the top of the sample where that heat is retained throughout the build and doesn't conduct away very easily. And you can see here we sectioned the samples and imaged them from the side, and you can see that solidification cracking here as well. So the titanium alloy, this was the most dense sample we made of this alloy. So its crack susceptibility is like completely off the charts. But it's an FCC alloy with brittle intermetallics, nickel titanium intermetallics, and a lathe phase in the matrix. And we see extensive solid state cracking. And you can see it didn't disappoint on this front in the weld tracks either. So there's extensive solid state cracking at every condition. And this cracking was so prevalent that it caused spallation of the surface, so we couldn't get any useful measurements from these alloys at all because the cracking was so prevalent. Lastly, we have this beautiful single-phase alloy, which printed beautifully. I showed some images earlier, and the weld tracks completely mimic that. I'm yet to find an etchant that works on this alloy, but you can see no cracks, so that's good news. So, onto my novel alloys. Well, here are some examples of ones that didn't go so well. So, these are BCC refractory alloys, as you can see, and the cracking morphology for each of these is quite different. But we haven't looked into these so much because the fact they cracked is enough for me for the time being. We also had some, here's some examples of the different types of cracking which we've seen in previous alloys. We also had some very optimistic results. So here's an alloy which unfortunately I can't disclose the composition because it's of interest to my industrial sponsor. But you can see that there's no cracking observed at any volume energy density. And also, we have some EDX analysis, which here you can see the weld if you can't see it very well. And also, the welding has resulted in homogenization of the microstructure versus the arc-melted sample. Much the same story with this alloy, which has zirconium instead of vanadium. And we had to etch this alloy also to be able to see the weld tracks. And the microstructure was pretty homogeneous in both the arc-melted sample and the weld. So this is our flow diagram. We have two pretty optimistic alloys. And our ongoing work is now involving the modelling and the AM. So just a quick insight into the modelling. We have got some alloys and we are able to measure the weld track depth amongst some other parameters. So we've done some direct weld measurement and used that to calculate various material parameters that can indicate cracking in conventional alloys. And we plotted some of those on this graph. So these 5 alloys were the only ones which I could get data from on this. So what we're doing now is using Rosenthal method-based simulations to be able to add to that database from known alloys. So we're simulating the weld track on known alloys, and then we can add that to this graph effectively. I'm also looking at the use of CalFAD to be able to predict the solidification cracking by using child-based equations. So just to summarise, I proposed a welding methodology for assessing AM processability, and we compared it with the HEAs which were previously manufactured by AM, and we've seen a remarkable similarity. And we found 2 novel weldable HEAs, and these are now going on to be manufactured by AM, both through pre-alloy powder and elemental powder in situ alloying. So with that, thank you very much. I'll take any questions.